Good day and welcome back for the fifth and final part of our discussion on integration by parts. As I mentioned at the end of the previous video, this is the time I would be turning the floor over to you as students if we were meeting in person. So hopefully you've already spent some time thinking of these three examples. If not, there's no better time than the present. Give yourself a solid 10, even 15 minutes and see what type of progress you can make. So working from the top down, the definite integral from 0 to 1 of the natural log of x plus 1. Our intuition is that inverse functions like natural logs, arctangents, arccosines are well suited for integration by parts. So let's see what happens. Our choice for u, thinking of liate, is going to be the inverse function. And dv would be forced to be just a 1. That means du is 1 over x plus 1, and v is x. So applying integration by parts, we have uv minus the integral of v du. And as we've seen, with integration by parts, the question becomes, can we evaluate this resulting integral? And we have several choices in this case. So one of them is you could substitute w equals x plus 1 and work the problem out. I'm going to go ahead and approach it in a different way just to give you maybe a slightly different perspective. And I'm just creating a little more space here. I'm going to think about this very intuitively. The question I would typically ask you as a student is, if you were allowed to add a number to x in the numerator, what number would you add to make this expression as simple as possible? And I know that's kind of a silly sounding question, but go with it. You would add a plus 1, right? If I was to, just for fun, put a plus 1, x plus 1 over x plus 1 is 1. But you can't do that for free. If you put a plus 1, you also need to put a minus 1. So how does that help us? Well, you can always break a fraction up over addition or subtraction in the numerator. So you could rewrite this fraction as x plus 1 over x plus 1, which is 1, minus the fraction 1 over x plus 1. So we have manipulated this integrand algebraically. And the reason we have done this is now we have a very reasonable integral to evaluate. An antiderivative of 1 is x, and an antiderivative of 1 over x plus 1, if we just look to the right, is ln of x plus 1. And don't forget your absolute value. And I just realized that this was a definite integral. And I'm sure we've all been in that position, right? We're evaluating a definite integral, we get down to the end, and we realize that we haven't taken those limits into account. Well, that's not a problem. We can easily fix this, just in real time. We go through and we need to evaluate in each step from 0 to 1, whereas at the end we just need a single from 0 to 1. So let's just go ahead and take care of this. Replace each and every x with a 1. 1 natural log 2 minus 1 plus the natural log of 2. Note the minus sign in that second piece needs to distribute. Then we're subtracting away what we get when we plug in 0. So 0 minus 0 plus the natural log of 1. And note, natural log of 1 is equal to 0. So we end up with 2 natural logs of 2 minus 1. And it is also worth noting that at the outset of the problem, you certainly could have done a substitution, say w equals x plus 1, and then evaluated that resulting integral. In either case, if done correctly, you would come to the same solution. For our next example, we have an indefinite integral of x times the natural log of x plus 1. We could apply integration by parts to this directly, but I do think it works out a bit nicer if we begin by doing a substitution. So let's let w be equal to x plus 1. So dw is dx. And note the situation we find ourselves in. We have this leftover x that we need to rewrite in terms of w. Very reasonable. When this happens, we just look at our substitution. X is equal to w minus 1. So our integrand is now w minus 1 natural log of w dw. And we're in an ideal scenario, not surprisingly, to use integration by parts. So u and dv. Because we have a polynomial and a natural log, our choice for u should be the natural log. If you think of that mnemonic device, liate, logarithms come higher up on the list than algebraic expressions or polynomials. So u is the natural log, dv is w minus 1. Going along with this, we would have v is 1/2 w squared minus w, and du is 1/w dw. So applying our integration by parts, we have uv. I'm going to write this as 1/2 w squared minus w, all multiplied by the natural log of w. And then we subtract away the integral of v du. And note, just to simplify as we go along, the 1/w in the du cancels off one of the w's in each term of the v. So those would combine together algebraically to be 1/2 w minus 1. And our resulting integral is very reasonable. So just kind of cutting and pasting down this first term, and then anti-differentiating term by term. So 1/2 times 1/2 w squared. And then we have this minus sign out front, so I'll go ahead and put parentheses and we can distribute later if we want. And antiderivative of minus 1 is minus w, and then a plus c. And our final step is hopefully the easiest step, but maybe the most tedious to write down. Each and every one of these w's needs to be replaced with an x plus 1. And that gives you the following. And this completes our second example. Now note, for extra practice, you could certainly rework this integral without initially doing that substitution. Applying the substitution first, I think, makes this resulting integral along the way a bit easier for us to evaluate. Moving on to our third and final example, dealing with integration by parts, we have the antiderivative of t secant squared. And this is something that looks extremely reasonable for integration by parts, because it's t times a function, and the function is something we can integrate. So for integration by parts, it's very reasonable to try u equals t and dv secant squared. Then du is dt, and v is tangent of t. Note, if you're thinking back to liate, which we've referred to several times now, that helps you to come up with your choice for u. In our case, a polynomial is an algebraic function. Secant squared is a trig function. So the polynomial is higher in that list for liate, so we're going to try that for our choice of u, and plus it just matches our intuition. Integration by parts gives us t tangent t minus the integral of tangent. And note, tangent is a function that we've integrated recently. We did need to wait to calculus 2 because its antiderivative is going to involve a natural log. It's not something that I suggest you memorize. Remember, our memory space in a sense is finite. What is better in many scenarios is to remember the technique we would use to evaluate the indefinite integral. And if we simply rewrite in terms of sine and cosine, we can maybe see that there is an appropriate substitution. If u, and let's call it w, is cosine, dw would be minus sine dt. We have a minus out front. If we make that minus out front a plus, we can pull the minus inside, so that minus sine t dt is our dw. So continuing on, writing each term using good notation, organizing our work in a single vertical column, we're left with anti-differentiating 1 over w. The antiderivative of 1 over w is natural log absolute value w, and we have our plus c. And we finish once again with a substitution. Which completes our current example, and it also completes our discussion on integration by parts. So make sure you're looking through suggested problems and don't just blindly apply integration by parts. Instead, make sure you're thinking in each and every problem, what is the best approach and why am I applying integration by parts? Because remember, as we discuss more and more techniques of integration, which we will be doing over the coming sections, we will eventually have problems where we just say integrate the following, and parts A through E. Your choice is going to be what technique of integration to use. So we want to build up the thought process, which we will hopefully focus on each and every section. So stay tuned and take care.